Hello ladies and gentlemen, this is Ms. Skokin. Back in Chapter 7, which is all about similarity, and this time we're going to be talking about properties of similar triangles. Our lesson objectives are: use properties of similar triangles to find segment lengths, and apply proportionality and triangle angle bisector theorem. You can see that we have some new vocabulary, so take a look at that, and then I'm going to ask you to pause the video, work on the warm-up questions, and turn the video back on when you're ready to check your answers. See you back in a minute. Hopefully you remembered your algebra skills and solving proportions and you were able to solve all four of these successfully. Just remember to pause the video if you didn't and copy down this work, take a look at it, figure out your mistakes if you have any, and then ask in class if you need some help. You can see that we have four different images here, and if you look at them, they are all different examples of perspective drawings. Notice that the smaller an object appears in the picture, the further away it seems to be. We can see this from all of the different images here, even in that checkerboard floor that looks like it goes off into the distance. This is called perspective, and this allows us to make two-dimensional pictures look three-dimensional. Believe it or not, this is an example of geometry at work. Now let's take a look at the triangle proportionality theorem, the first theorem from this section. This theorem says if a line parallel to a side of a triangle, such as we've got right here, intersects the other two sides, then it divides those sides proportionally. So you can see in our image, we've got a side BC, which is parallel to this line EF cutting through our triangle. And what this is saying is our side AE has the same relationship to EB that length AF has to FC. We can see that in the conclusion of our theorem. This is going to allow us to solve problems associated with a triangle that is cut proportionally by this type of parallel line. Let's take a look at example 1 on the next page. The instructions for example 1 say, use the triangle proportionality theorem to find the length of US. Just as in the description of the triangle proportionality theorem, we have a segment that is parallel to one of the sides of our triangle. And that means that our triangle is cut proportionally. So RU is to US as RV is to VT. Let's set that up in a proportion. Once we've got the proportion set up, it's easy to plug the numbers in. Remember that we don't know what US is, so we can either keep US or we can put in a variable to represent our unknown. Once we've got the proportion set up, we can use our cross multiplication to solve the proportion. Remember to always simplify before you multiply if you can. It makes it makes proportions just a little bit easier to solve if you don't have a calculator available or if you're not allowed to use one, such as on some of our standardized testing. Next, we have a now you try, which means you're going to be turning off the video, working on this question, and then turning the video back on to check your answer. See you back in a minute. As always, we want our final answer either in a mixed number or in an improper fraction. If you have any questions about this one, bring them to class. Here's our next theorem, converse of the triangle proportionality theorem. And just a reminder, converse theorems reverse the hypothesis and the conclusion. So in this case, what we're trying to do is to prove lines or segments are parallel using the fact that we know that the sides are proportional of the triangle. So the theorem reads, if a line divides two sides of a triangle proportionally, then it is parallel to the third side. Remember, our if-then is reversed, and what we're trying to do is to prove that a segment or line is parallel to one of the sides of our triangle. Let's take a look at example 2 on the next page where we will be using this theorem. Example 2 reads, using the converse of the triangle proportionality theorem, verify that segment DE is parallel to segment BC. This means we need to start out by checking to see if our side lengths are proportional, and if they are, we can prove that the lines are parallel using that theorem. When we set up our proportion, it's going to have a little question mark over our equal sign because we're not sure if they're proportional, but we're checking for it. So we want to know if BD is to DA as CE is to EA. Now let's plug in the numbers. We plug in the numbers and simplify. Both ratios are 3/2. So this means we are able to prove that segment DE is parallel to segment BC using the converse of the triangle proportionality theorem. We've got another Now You Try for you to practice your new skill. So using the converse of the triangle proportionality theorem, you want to verify that segment MN is parallel to segment KL. Good luck. Turn the video back on when you're ready to check your final answer and move on. As always, if you do have some questions about this one, bring them to class. What happens when there are more than two parallel lines? And we can see what's happening with the diagram where we've got three parallel lines and two transversals going through them. We remember from previous chapters that we have corresponding angles and alternate interior angles that are all going to be congruent, and same side interior angles that are going to be supplementary. But in addition to that, we have this new relationship that will divide the transversals proportionally. We can apply this to triangles, and we'll see that in the next example, in example 3 on the next page. An artist used perspective to draw guidelines that would help her sketch a row of parallel trees. She then checked the drawing by measuring the distances between the trees. You can see that we've got 4 trees that are parallel to one another. Those end up being the parallel segments, and we've got 2 transversals. Those are the dashed red lines on the top of the trees and at the bottom of the trees. Question A says, using the information in the diagram, find the length of LN. Knowing that these trees are parallel, we can use the proportionality of the triangles to find the missing length. We're going to start by setting up the appropriate proportions. We want to find LN, so that means we need to use the corresponding sides on the opposite side of the triangle that these parallel lines cut through. So that means we're going to be using from B to D. We also have the lengths between K and L and between A and B. So that'll be our first ratio. AB is to BD as KL is to LN. Next, plug in the numbers. Let's add the lengths from B to C and C to D first. Now we've got a proportion we can easily solve. Remember that this is a drawing, so when we get the distance LN of 3.9 centimeters, don't let that surprise you. This is a drawing of trees, not actual trees. But we did use triangle proportionality to be able to find the distance from L to N. Now let's tackle part B, which says find LM. Again, we're going to set up proportions. This time we're going to say AB is to BC as KL is to LM, which is the one that we're trying to find. And of course, now we plug in the numbers. Once we plug in the numbers, it's an easy proportion to solve, and we're able to see that the distance between points L and M is 1.5 centimeters on the artist's drawing. That leads us to our next theorem, 7-4-4, the triangle angle bisector theorem. This theorem says an angle bisector of a triangle divides the opposite side into 2 segments whose lengths are proportional to the lengths of the other 2 sides. This sounds a little complicated. Remember, an angle bisector breaks an angle into 2 exactly equal pieces. This says that when we have an angle bisector in a triangle, it's going to create sides that are proportional. So the opposite side is going to be broken up into 2 segments, BD and DC, that are proportional to the lengths of the other two sides, AB and AC. Let's take a look at the conclusion. BD is to DC as AB is to AC. So again, we have to have partners, and BD and AB are on the same side of the angle bisector. DC and AC are on the same side as the angle bisector. So in proportions, this is just a quick reminder, if we have A over B equals C over D, then we end up with AD is equal to BC. But if we have A over C equals B over D, we're going to end up with AD is equal to BC. So as long as our partners stay in the same places, either in the same fraction or both on the top, then our proportion is going to work out exactly the same way. So just keep that in mind as you go through example number 4. In example number 4, of course, we're using the triangle angle bisector theorem, and our instructions are to find the lengths PS and SR. We can see that we have an angle bisector at angle Q, and it created a segment that divided the opposite side PR into proportional segments. So we're going to start out writing our proportion as PS is to SR as PQ is to QR. From here, we plug in the expressions. And just like we've been doing for the past few lessons, now we just have a proportion to solve. Just a reminder when we're solving these proportions that first step is crucial. Do not try to do that distributive property in your head. Write it out. Because once we've got that proportion set up and we do the distributive property, the rest of it is just relying on our old Algebra 1 skills. So we can easily solve this. And once we find the value of x, which is 30, we plug back in to the expressions for PS and SR to find our missing values. We've successfully found the missing side lengths of our triangle, and we're ready for a now you try. Remember that you're going to pause the video, work this out, and turn the video back on when you're ready to check your final answer. If you have any questions, of course, bring them to class. Good luck. Again, as in all the previous examples, it's all in the setup. Once you've got that, you can solve the proportion very easily. Well, that is it for this lesson. So you've got some independent practice coming next, and I recommend you first have the theorems in front of you to look at, and then try to do the problems without the theorems in front of you, because it is important that you remember these relationships by memory so that you can do a great job on your upcoming test. See you back in class.